Good afternoon to another lecture in the basics of macromolecular crystallography. Today we are going to look into the other phasing method, experimental phasing. Now, experimental phasing is all about intensity or reflection differences, which we use to find certain atoms. In the case here in the title slide, these are the sulfurs that form disulfide bridges. But it's always about using intensity differences to get phase information. As a short reminder, in the beginning, I'm going to talk about the phase problem. So, as you know, electron density is a three-dimensional, steady, and continuous function of which we can make a Fourier transformation. And hence, they can be expressed as a Fourier series of structure factors called FHKL. If we know all the structure factors, including their amplitudes and phases, we can do a Fourier synthesis and get the electron density, and from this solve our structure. So this is what we want. Now, a structure factor can be seen both as a wave, in which case the amplitude is, well, the amplitude of that wave, and the phase is where it goes through zero. It can also be seen as a vector in the complex plane. So if you imagine you have, well, the imaginary axis here and the real part here, you can regard this as a vector in complex space, in which case the length of the vector would be the amplitude. And the angle over the real axis would be the phase. The amplitudes we derive rather straightforward from the intensities we measured. The amplitude squared is proportional to the intensity, so we have this from our measurement. However, the phase cannot be measured directly, albeit it can be derived, as I'm going to show in this lecture. And because it cannot be measured directly, we have what is called the phase problem, the central problem of crystallography. Now, what exactly is experimental phasing? Experimental phasing methods depend on intensity differences. These differences are caused by a marker substructure of certain elements. This is sometimes called heavy atoms, marker atoms, or substructure. However, it's a discrete number of atoms and not the entire macromolecule, but only some subset. Which subset exactly depends on the wavelengths, the experiment, and the phasing method used, but all experimental phasing methods exploit some kind of difference that is only generated by a few atoms to derive from this information the positions of all atoms. MAD and SAD, multiple anomalous dispersion and single wavelength anomalous dispersion, exploit the anomalous signal. What the anomalous signal is, I'm going to explain in a moment, from one or more data sets of the same crystal. SIR, single isomorphous replacement, a special case radiation-induced phasing, and MIR, multiple isomorphous replacement, use several heavy atom-soaked derivative crystals. So you have your crystal, for example, of lysozyme, and you soak it with, say, heavy metal compound, say zinc, and use then the original type of crystal and the soaked crystal. You measure data sets of both of them, and then you observe how the intensities have shifted from one to the other. So this is why it's called isomorphous replacement. The crystal basically stays isomorphous, and the heavy atoms constitute the only difference. MAD and SAD methods use only the signal from usually one crystal and exploit anomalous scattering. And in this lecture, I'm mostly going to talk about anomalous methods because they're more popular today. But basically, SIR and MIR methods work the same way. So you can deduce from the SAD and MAD methods how SIR and MIR work. And again, I would like to recommend to you Bernhard Rupp's book, which covers this in great detail and also uses some of the examples I'm going to show in this lecture. Now, here's a short overview over all the methods in experimental phasing. SAD methods have a special case, native sulfur-based SAD, where you are exploiting cysteine and methionine, but mainly cysteine sulfurs that are native to your protein. So they are part of the 20 proteogenic amino acids. The sulfur is there. And these sulfurs make a very weak anomalous signal. But if you've got a very good resolution and very good measurement, you can exploit those sulfurs in order to phase your structure. Multiple wavelength anomalous diffraction is stronger and uses information from different wavelengths. However, you'll have to have a crystal that withstands having several data sets taken off it at different wavelengths, and sometimes your crystal will just succumb to radiation damage. Single isomorphous replacement and radiation-induced phasing, RIP, I already talked about. Multiple isomorphous replacement, and then all of these methods can also be combined at random with each other, giving you methods like CIRAS or MIRAS. Now, anomalous scattering. Remember that structure factor? Here it is. So you've got a complex plane, and you just assume that every atom adds a little bit to your structure factor. This is actually the case. Every atom in your unit cell makes some contribution to any given reflection. So after you take the contribution from each atom and you add them all together in a sum, what you get is the total structure factor for that reflection. Friedel's law was found relatively early, and they basically showed first that the intensities of two reflections that were centrosymmetric to each other. So one had the random position HKL in the reciprocal lattice, say 1, 2, 3, and its Friedel made the reflection with the index -1, -2, -3 had the same intensity. So Friedel's law says that the amplitudes of two reflections that are centrosymmetric to each other in reciprocal space must have the same amplitude. Their phases must be exactly opposite. So you can see this here. You have the structure factor of HKL here, and its Friedel mates there. And as you can see, their length is the same, but the angle of this one is exactly the opposite of the angle of the latter one. However, Friedel's law only held a few decades. Long time, people assumed deviations from Friedel's law were only experimental errors. But then a guy called Byfoot found some systematic to this. And he postulated that there is anomalous scattering, which breaks Friedel's law essentially. So if you've got an atomic contribution, small f, you have F0, which depends solely on resolution and element in question. And then you have F prime and F double prime, which are the real and imaginary component of the anomalous signal. Now, usually they're very weak and cannot be observed. However, close to the absorption edge of the atom's element, the atom that is causing small f, they can become rather large. Hence, they are wavelength dependent. F prime and F double prime cannot be observed just everywhere. They can only be observed at wavelengths that are very close to where the atom, the element, is actually absorbing X-rays. This is a plot, and if you ever do experimental phasing, you'll stare at these for quite a while. It has energy in one direction and wavelength, of course, in the opposite direction. So imagine this to be the wavelength range of the beamline you're measuring at. If you're measuring at a home source, you will only have one wavelength and you cannot change it, which is why a synchrotron beamline is the best place to measure anomalous data sets, in most cases. Now, here is F double prime. And as you can see, as the energy increases, it peaks and then it slowly goes back. And if we would like extend this plot 2 meters to this direction, it would possibly come down again. F prime, however, just makes a minimum and comes back up to its original value. This will be of importance later when we look into measure strategies in the end of this lecture. However, for now, you should just know that at the absorption edge, F prime and F double prime do pretty extreme things. And that if you ever need a fluorescence, if you ever need a plot like this, you can go to Skuld bmscwashington.edu. The Skuld server makes you theoretically curves that can be calculated for each element. Or you can measure a fluorescence scan of your crystal, and I would highly recommend that. I think I also have a picture here. Oh no, I don't. Interesting. So F double prime, the thing that's plotted here on top, breaks Friedel's law. Here are our two Friedel mates, F HKL and F minus H minus K minus L. Now, if we sum up all F prime contributions for each atom that is contributing to the structure factor, we get the sum over all F primes, and that usually points backwards, making the amplitude smaller. Now, at the right angle to this is the sum of all F prime double prime contributions. And these F double prime contributions now make our structure factors different in length and also different in phase angle. The latter is not so important for anomalous phasing, at least not for the user. The first is really relevant because that means that now between two Friedel mates, you can measure a difference in amplitude. And that difference is only caused by whatever element at the wavelengths you measured at had an absorption edge. So it's only caused by few atoms, and it's an intensity difference, and hence we can use this to do experimental phasing. This is also used in small molecule crystallography for absolute structure determination. It is basically used to decide on the chirality of a compound. Now, in biology, we don't have this problem because, as we have already had in this lecture, all the proteins have the same handedness, as they only occur as such in biology. But in small molecule crystallography, absolute structure determination is very important. And when Emil Fischer postulated these things, he didn't have X-ray crystallography. It did not yet exist. Luckily for us, so he could only determine the relative chirality of compounds. But luckily for us, he just guessed correctly. Otherwise, by the time that X-ray crystallography came into the game and the first tartrate or chiral structures were determined, we would have to change all our textbooks to make every three-dimensional depiction of atoms and molecules be the other way around. But luckily, Emil Fischer was right. So the first step to do this, and I'm following some SHELXC routine here, is how to find the substructure. Now, we find the substructure means we find the atoms, for example, the sulfurs or iodines or zincs that gave us the anomalous signal in this case. And in this lecture, I'm going to explain things a little bit from a SHELXC point of view, because SHELXC is one of the more widely used programs for experimental phasing, and also because I'm kind of a specialist in it. However, what I say is generally true for all of the programs and should be useful even if you're using different software. Now, SHELXC has 3 programs, SHELXC C, D, and E. C does the alpha angle calculation, data analysis, and file preparation is usually run first. So you take your experimental data, you take them into SHELXC C, then you do substructure search, which is done by SHELXC D, and then density modification and tracing, which is done by SHELXC E, and then you are there. You've phased your structure, hopefully. Now, how do we find the substructure? I know this is the second step here, but I'm going to start with it because kind of logically, it's the first one we want to consider. How do we find this? Well, we use an old friend, the Patterson map. You remember from structure factors, you can calculate electron density. But if you, these are amplitudes and phases, but if you don't know your phases, you could still set all the phases to 0 and still do a Fourier synthesis. So if you take the intensities and set all phases to 0, you get a Patterson map. We've talked about this 2 weeks ago in a lecture about molecular replacement. Now, however, this can look very, very crowded for a macromolecule. And if you're not doing molecular replacement, it's not going to help you to find your anomalous scatterers. So in order to find your anomalous scatterers, what you do is you take only the information that comes from them, meaning you take the intensity differences and you set all phases to 0. What you get is a map of peaks that only relates to the distances. Remember, the Patterson gives you information about distance and direction of this distance between two atoms. You only get distances between your anomalous scatterers. And while you may not be able to derive your entire structure from your Patterson map, you can use the anomalous Patterson to find the 6 or 8 or whatever anomalous scatterers you have. And in the old days, actually, people would sit and by hand interpret their anomalous Pattersons. This is then called an anomalous Patterson map. So in order to find the substructure of marker atoms, we can use these Patterson methods, or we can use something else that small molecule people are also using to solve their structures, direct methods. So we borrow them from small molecule crystallography, but instead of using intensities, we only use intensity differences, for example, between two Friedel mates, or between two isomorphous crystals where one has been soaked and the other has been not. These methods require separate atomic electron densities to locate atoms, which clearly would not be true for all the atoms in a macromolecule, but the marker atoms have relatively large interatomic distances. Now, if you think back to my title slide, that's not always true, is it? Because you have, for example, in sulfur set disulfide bridges. So the two sulfurs are relatively close to each other. And at, say, 3 angstrom resolution or 2.5, you may not be able to resolve them from each other. And, well, there's a little like patch that experimental phasers do for this. We just call them disulfide super sulfurs and treat them as basically two sulfurs piled on top in a rather elongated peak. And even though this seems like very ramshackle in a way, it's like really strange approximation, it made a lot of structures phasable that weren't before. Now I'm going to quickly just brush by direct methods. There you use the fact that the phases of strong reflections are related because the atoms are not randomly distributed. So first of all, two atoms cannot be on top of each other because, well, van der Waals forces repulse them from each other. The other is that electron density is never negative. If you exploit this, it means that the phases must have certain values and cannot have certain others. And this gives you the triplet equation and the Sayre equation, which are basically saying the same thing. There are also things like quadruplet equations, and this helps to find a structure. These relations are relatively easy to resolve for a few atoms. And also in direct methods, you use normalized structure factors, so-called E-values. Now, you should have heard E-values before in this lecture series when we were talking about twinning and data statistics. The E-value squared for each reflection is the amplitude squared divided by a scale factor, which is usually 1, and then divided by all other such values in the same resolution bin. So you're basically resolution-wise normalizing your intensities, and that is what an E-value is. It basically refers to point scatterers instead of atoms with a B factor and a Gaussian distribution. Here are two terms that you should be familiar with. Patterson seeding means to start from positions that are already consistent with the anomalous Patterson that has been observed. And dual-space direct methods is a special kind of direct methods that recycles and modifies trial structures in the electron density map, which is arbitrarily calculated, it's not clear if it's correct, and then refines the phases back in reciprocal space. And this converges much, much faster than normal direct methods would. So substructure search, say you have 7 atoms and you've measured 5,000 Friedel mates, or 10,000 to get 5,000 differences. Substructure search, hence, is an overdetermined problem with noisy data. What exactly do I mean by this? Well, we want to find 7 atomic positions That would be X, Y, and Z. So 7 times 3 is 21 parameters to determine in an equation system, where our measurement values are 5,000. But these 5,000 are only the difference of 2 intensities, and hence they're very noisy. So it's an overdetermined problem because we have so many observations, but the data are very noisy. An overdetermined problem with noisy data. You should keep that in mind because it needs to guide how you measure and select your data for experimental phasing. Critical factors are the resolution range highly affects the outcome. So you need to choose the correct resolution range, which is typically not your full resolution range. So if your crystal scatters to 1.6 angstrom, the anomalous signal is only a fraction of the intensity, right? Is only the difference between 2 intensities. So you may find that your anomalous scattering only extends to 2.2 angstroms. You need a very good data quality. So experimental phasing, in particular sulfur SAT, are kind of like the crown of data measurement. It's basically a litmus test if your beamline is fine. If a beamline can do sulfur SAT, usually nothing major is wrong with it. Intensity outliers are problematic. Think, for example, that the beam stop during your measurement obscures a reflection, but the beam stop mask is not accurate, so you're integrating over that reflection. But then after 180 degrees, the Friedel mate is not behind the beam stop, but fully there. Now the difference that would result from these 2 reflections, where the first one has been wrongly assigned a near 0 intensity value, would be huge. So you need to totally avoid these things. It can break your entire experimental phasing. I've seen it several times that, you know, taking out 1 or 2 reflections that were pathologic could actually make a structure solvable. So great care has to be taken during integration and scaling. Anisotropic scaling, which is now usual and very common, is also needed. However, even if you can find your substructure using the anomalous Patterson and dual space direct methods, the handedness is not resolved at this stage. So you get, of course, 1 substructure, but whether that's the correct solution or the enantiomer of that, you don't know. You actually have to employ both in all steps that are to follow. And this was also possibly the reason for one of the biggest withdrawals of papers that we had in macromolecular crystallography. Look it up when you have coffee break or something. So how many atoms do we search for? Actually, you need to tell the program usually how many atoms to search for. Certainly improves your chances of success. So how many? Well, if you've got sulfurs, it's pretty easy, right? It's the number of sulfur atoms. But wait, disulfides should be given as 1 instead of 2 peaks at any resolution smaller than 2 angstrom, because that's the distance between the 2 sulfurs. So you need to do a little bit of calculation. If you soak your crystal in iodine, which is called iodine squishing, because it's so fast, you take the number of amino acid residues in an asymmetric unit. So not only in your monomer, but times how many monomers you expect in your asymmetric unit, divided by 15. And if you do rip phasing, the number of disulfide bridges is also a good starting value because they crack open first. And how do you know if the substructure search worked? Now, this is a huge problem. Anyone has a good idea? We'd love to have a better indicator here because it's really super hard to tell if it worked at this stage. Very often you just have to continue and hope it was correct. So we use a CFOM combined figure of merit, CFOM, get it? Which is CC all and CC weak. It's the correlation of the substructure, the reflections you would expect from the substructure, and the reflections that you've measured. And sorry, I don't mean reflections, but the anomalous differences. So CC all is the correlation between the anomalous reflection differences you would expect from your measured data, sorry, I'll have to start again. CC all is the correlation between the anomalous differences you expect from the substructure you think you have correctly and the ones that you've actually measured. And CC weak is the same thing, but only for the weak reflections, which remember, have not been used in direct methods and have little influence on the Peterson, so they're kind of independent. Both of these values need to be high, and you can see them here plotted against each other. So this is CAC all and CC weak. And if you see something like this, a distribution of hits here with low values and then other hits here with high values, and if they separate nicely, usually the thing that separates nicely at high values is correct solutions. So that's a very good sign, but it's not exactly super well accurate and scientific, so we would like a better indicator, please. You should also see a clear drop in marker atom occupancies. If you want to try this for real, I can post in the Telegram chat a link to a tutorial, which you can do at home. Or if you have a substructure with known geometry, for example, you employed a tantal bromide cluster or a magic triangle, you'll know where your anomalous scatters, how they should look, right? They should be close together, they should form a geometric pattern, you'll recognize them. So if you see this in your substructure, which has been found arbitrarily, it's pretty sure that at least this part is correct. However, the ultimate indication is a successful density modification resulting in an interpretable map. Now, phasing the rest, SHELXC. So this is in nature, in usage of the program, the first step, but here's the second, because logically, you want to talk about it after you know your substructure. So, remember our friend FHKL. FHKL, or F total as it's called here, FT, can be seen as a sum of all the atomic contributions from the protein, called FP, and all the contributions from the iodine, FA, F of anomalous scatterers, or marker atom contribution. The sum of the two of them, so FP plus FA, gives you F total. The angle between FA and F total, we call alpha. Why that's useful, I'm going to show in a moment. So we have alpha, and it's an angle between the marker atom structure factor and the total structure factor. Now, alpha is hence defined as the phase of the total structure factor for this reflection minus the phase of the anomalous contributors. Now, that's not very useful because we don't know those. But if we know the substructure, if we know the positions of the anomalous scatterers via Fourier, we can calculate their phases. So we know the phase of the anomalous scatterers, and then if we can estimate or calculate alpha, we can get the phase of the entire structure factor. And if we can do this for all our structure factors that we've measured the amplitudes for, we get, well, a solution to the phase problem. Now, here's the mathematical way to describe this. Given there are no errors, and you don't need to use likelihood, these are the phasing equations. So FT is the total structure factor, FA also is their marker atom structure factor, and remember alpha is phi T minus phi A. So these look rather complicated, but if you look here, this would be the intensity of HKL, and this would be the intensity of minus H minus K minus L. And then there are three factors, A, B, and C, and F on the anomalous scattering, so their values are large, near the absorption edge, and negligible anywhere else. So for each wavelength, you will have different A, B, and C, and two observations, FHKL and F minus H minus K minus L. The amplitude of the anomalous scatterers, the amplitude of the total structure factor, and alpha are your unknowns. So given good data from at least two wavelengths, you can solve a system, where you have three unknowns because you have then measured four measurement values. Four measurement values, three parameters, fine. That would be mad. Multiple anomalous dispersion, multiple wavelength anomalous dispersion, and it works best if the F prime and F double prime values are large, because remember, that's what makes these different. In a SAT experiment, you only have two observables. but you still have three things you want to determine. So you need to make an approximation, and the approximation you make is you basically say that the total structure factor is the middle value between FHKL and F minus H minus K minus L, which is good enough, sufficient for substructure solution and estimation of phi t. Now, I imagine that this was rather complicated. The phasing equations are not for faint of heart. However, we are now going to do this graphically. This is also not particularly easy, but I hope it's better understandable than the equations. However, it depends. I already had people tell me that they found the equations easier. If you've got trouble following this, I would strongly recommend taking the YouTube video of this lecture, pencil and a ruler, and doing this graphical reconstruction yourself. Once you've drawn it yourself, it's typically pretty clear. Remember, we have the protein contribution, the anomalous scatterer contribution, and then we have F prime and F double prime. F double prime is, as always, at a right angle to the F prime contributions. And we have the angle alpha between the total structure factor and the anomalous contribution. This is the basic geometry we're going to use. Now, imagine we observe this. FHKL, the amplitude of FHKL, the intensity that's related to this, is much larger than the Friedel-Mate. So we could say the amplitude of FHKL is much larger than the amplitude of F minus H minus K minus L. What does this mean for our angle alpha? Here's the same construction as we had previously. F minus H minus K minus L is small, FHKL is large. This can only have happened if the F double prime contribution made F minus H minus K minus L smaller and FHKL larger. And that has implications for the alpha angle. In order for this to happen, it must be close to 90 degrees. If it would have been larger, the difference would have been smaller. And if it would have been close to zero, it would also have been pretty small. In order to see a very big difference between two Friedel-Mates, the alpha angle of these must have been close to 90 degrees. Because F double prime has to point, the sum of all F double prime contributions has to point in the same direction as FHKL, and F double prime of the Friedel-Mate has to point in the opposite direction. Now, if the opposite is the case, FHKL is much smaller than its Friedel-Mate, alpha must be, for the very same reasons, close to 270. So after indexing our system and integrating it, if the Friedel-Mate's difference is large, and depending which one is larger, FHKL or F minus H minus K minus L, we can say something about the alpha angle. It needs to be 90 or respectively 270 degrees. As you can see, this approximation is very rough. We could never tell if it's like 80 or 100 degrees, but it's, well, an assumption that will be approximately true. However, what happens if the two observations are similar? In this case, alpha cannot be close to 90 or 270 degrees unless the F double prime contribution is really small. So either F double prime contributions for these two Friedel-Mates are really small, or they're almost perpendicular to FHKL or F minus H minus K minus L respectively. So that means that we can assume that our alpha angle is 0 or 180 degrees, and which one we do not know. And this, by the way, is reflective of the fact that we cannot resolve handedness at this early stage, about which I'm not going to go into detail in a 1-hour lecture, but could possibly fill a few lectures with experimental phasing. Now, using this alpha angle, you can now compute the phase of the total structure factor, because you know the phase of the anomalous scatterers for this reflection. You know the alpha angle, or you have some assumption, at least for some of them. And because you know those, you can calculate the phase for the structure factor and get an initial map. That map will be very, very bad, really crappy, but you may go somewhere, in particular if it's mad. If it's sad, nothing can be done without density modification. However, you first apply sigma A coefficients and sim weights. Randy Reed has some excellent material on his homepage about these things. So if you want to go into detail here about the statistics, also the phasing equations with respect to errors, so taking phasing equations, taking errors into account, look at his homepage. It's really nice material, very mathematical, but he starts really from simple beginnings. So with school math, you should be able to do it. And now density modification. The phases are still ambiguities and they are inaccurate. Remember, for about half of our reflections, we were not even able to say if alpha is 0 or 180. Density modification dramatically improves these initial phases, and it also resolves the handedness problem, as long as you think about using the substructure in both forms. Now, what does density modification do? If you think of the electron density of your crystal, is there a difference between the macromolecule and the disordered solvent? And if so, what do you think that difference is? The disordered solvent is pretty uniform, while the protein region has peaks at atomic positions and, for example, between two beta sheets, also minima of electron density, so it's much more varied. This can be exploited in order to improve phases in real space. So we take the electron density and we basically make it look more like protein in order to improve our phases when we convert back to structure factors. The solvent area is flattened or flipped. NCS averaging can also help you, and a high solvent content is often better here. While usually it's bad in almost any regard, making your crystals low resolution scatterers and squishy, here it's good. So I made a sketch on how density modification works in SHELXC, which uses sphere of influence. So you have your beautiful, ugly, newly generated map. It's kind of like a newborn baby. Yeah, it looks beautiful to you, but not to anyone else. And you ask yourself, is this peak in electron density I'm seeing here an atomic position? Mind you, this has nothing to do with the marker atoms that you found earlier. It's just some peak position in your new electron density. You draw a sphere around it. As this display is only 2D, I'm only drawing a circle, but imagine a sphere. It has 2.4 angstrom radius. Why is that? Well, 2.4 angstrom is the typical distance between 1 free atoms. So 1 atom, 2 atom, 3 atom in proteins, the first and the third are usually apart 2.4 angstrom on average. Now, if the middle thing was an atomic position and we are in the middle of protein, some other atom is likely going to lie somewhere on the sphere of 2.4 angstrom radius. So we plot the electron density on the surface and we look how much it varies. If it doesn't vary very much, the atomic position was likely not an atomic position inside the protein. So we flip the density, combine it with the newly calculated density later, which gives us something very close to 0 and very flat. If it varies a lot, like here, we sharpen the density, making the maxima higher and the minima lower. So as you can see here, there would be 1, 2, 3 atoms lying on the surface of the sphere, indicating that you're likely going to be inside the protein now. And so you want to sharpen this density. After we do this for many cycles, and we do this, of course, once for one hand of the substructure and once for the other, we get one that looks like protein. The other has little connectivity and looks ragged. If you're not sure what I mean by this, have a look into Bernhard Rupp's book. It's really excellent depictions there, or ask me in the Telegram chat. After density modification, the structure is solved. You can now start doing auto building. Hopefully it's going to work. Hopefully your map looks like protein. If your map doesn't look like protein, you have bad luck and have to start all over. But usually experimental phasing has led to initial phases. I'm going to quickly show you the free lunch algorithm, which is what you do if you cannot do auto tracing in SHELXC, about which I have also almost not mentioned. So in addition to density modification, SHELXC also does auto tracing to improve the phases, but it can do so only for protein. That's possibly going to be changed soon by Isabella Son and her team. I'm very much looking forward to this. But until then, if we solve RNA structures, we have to use the free lunch algorithm. There, you take all the reflections you did not measure, possibly even to higher resolution than you did measure, and you guess their value, which is basically making something out of nothing. Or, you know, there's no such thing as a free lunch. This improves the density for miraculous reasons. First, we are correcting Fourier truncation errors. You remember the little ripples I showed in one of the first lectures. Phases are the major influence, so if they are correct, actually amplitudes don't matter so much if they're a little bit off. And 0 might just be a bad estimation for an intensity that hasn't been measured. This is particularly useful for nucleic acid, and here's a rather extreme example. This is a map that had very, very, very low completeness due to an error. They had thought it's orthorhombic, but it was really monoclinic, so they had only a pizza wedge of the reciprocal space covered. And as you can see, the map was hard to interpret. The stick model is in there, so you can see what's going on, but of course they didn't have that. Now, after free lunch, to 1 angstrom, the map looks beautiful. Now, as I said, this is a pretty extreme example, but it shows you how useful this algorithm can be. In order to decide whether SHELXC has worked, you need to judge your connectivity. So you want continuous stretches, like continuous blobs of electron density representing the connectivity in the macromolecular chain. You want a high map contrast, meaning a clear separation between ordered macromolecular structures and the disordered solvent regions. And of course, the correct hand is the one with the higher map contrast. So if you're not sure by looking at them, take the one with the higher map contrast. However, in some space groups, be warned, if you only have one heavy atom, there are several space groups in which both solutions will give you the right hand because, well, if you only have one atom, the other hand of that atom looks exactly the same. The best indication for successful density modification is a map that looks like protein and in which the macromolecule can be built easily. I cannot repeat this enough. I wouldn't look so much to automatic conclusions. There is no like royal way to getting your phasing done automatically. You need to look at your maps and judge them. That's very often the quickest way to decide whether your phasing has worked. Now some practical things last. In data collection, and we covered this in the beginning of this lecture series, high multiplicity is good, radiation damage is often bad, precise intensity measurements are good. Near the absorption edge, the crystal absorbs most energy. Therefore, radiation damage can be higher than it usually is. A fluorescent scan tells you if there are anomalous scatterers present in the crystal. It doesn't tell you whether they're ordered or disordered, but it tells you if they're present. So if the fluorescent scan comes saying there's no anomalous scatterers, you can stop any attempt of like anomalous phasing there because it won't work. Whatever you tried to soak in didn't go in, or you're at wrong wavelength, something's wrong. And you need a good low resolution completeness because low resolution reflections, the ones close to the beam stop, are going to give you the largest intensity difference values and the most reliable too. Now, map data collection strategy. This is very debatable. There are people who do this differently from me. So I'm just going to give you my homebrew recipe and then you can decide whether you want to follow it or watch a few more lectures. I really recommend watching lectures about measurement strategies, for example, from Gerard Briconia. It's going to educate you before you go to the synchrotron. First, I would recommend to collect a peak, at least with a multiplicity of 4. Peak is where F double prime peaks here. Then Radiation damage, stop and try SAT phasing. If you have a second crystal, then go on and collect a high energy remote with it. High energy remote is well at high energy. If you've got no damage or second crystal, well, high energy remote. And last, measure inflection. Inflection is where F prime inflects, has its minimum. Radiation damage lowers the scattering power of your crystal. And if you remember, F prime contributions very often make the structure factor smaller, pointing backwards. So you're kind of artificially increasing the effect by measuring inflection loss. And then if you still have some juice in your crystal or more crystals, you can collect a higher resolution data set with lower multiplicity and a higher flux in order to use for density modification and refinement, where you're aiming for the highest possible resolution more than the best possible data quality. Your general data quality overall should be good. Multiplicity, completeness, RPIM. If scaling was applied, check your statistics, check your mask. Is your inner shell completeness good? If you have made a fluorescent scheme, keep it. This is usually done automatically at today's beamlines. Is there an anomalous signal in the collected data? You can look at CC anom, the anomalous correlation coefficient in scaling, D double prime over sigma, or D prime over sigma if you're doing isomorphous replacement. CC anom, the anomalous correlation of data sets. And then there are a few things that you also want to know before you start SHELXC. You want to know your space group. I cannot stress this enough. You need to know your space group. You also want to know whether you have a twinned crystal, which will make your life a lot harder. How many marker atoms do you expect, and which type do you expect? Which element? What could be the SHELXC resolution cutoff? If you've got really no clue, take the native resolution of the data plus 0.5. So if you've got 1.5 data, 2 angstrom is a good starting point. However, things like CC anom will give you a much better indication on where to cut your data. Could any marker atoms fuse into bigger blobs of density? Tantal bromide, disulfide peaks, anything else? Think about it and adjust your number of peaks you're searching for accordingly. Merging data from different crystals or runs. If you have measured, in particular, SAT data from multiple crystals, that may really help you over the gap. So I recommend merging isomorphous crystals. And actually, if you've got any questions about that, I recommend writing an email to Gianluca, who gave us a lecture earlier. He's a real-world specialist on the isomorphism of crystals and multiple crystal phasing. Expected solvent content and residue numbers, well, you need to know what your macromolecule is. Now, coming back to SHELXC. SHELXC calculates your alpha, which, as you've seen, you could estimate long before you know your substructure. Does your data analysis so you can decide on a resolution cutoff. SHELXC does substructure search, SHELXC density modification and tracing. Automatic tracing, by the way, if it works, which means the tracing structures having a CC of trace against native data over 25%, means that it's solved. And there's also the program Anoda, about which I'm going to talk in the end, which can be used for validation. Now, all of this can be put fairly easily in a pipeline, and there are a lot of pipelines for experimental phasing out there. If this doesn't work for you, I would strongly encourage you to use different experimental phasing programs, in particular such that use like sharp likelihood terms and take errors into account better. There's a very nice list of possible programs here on the CCP4 wiki, which is something that I generally would recommend reading. MRSAT is, I'm now going to come to a few like spin-offs of experimental phasing. MRSAT is what you do if you don't have enough phase information from SAT alone, but you have some like molecular replacement solution that is only partial or has severe model bias. You use the molecular replacement to bootstrap your SAT phases, which, by the way, also means that if you get a solution, you don't need to look for the second hand because you already used something chiral to begin with. And you knew it had the right chirality because proteins only occur in one hand. So it looks, for example, like this. This is a phaser result from Archimboldo. The map is shown as 2 sigmas. The TF was high, indicating a correct solution, but it would have been very difficult to build anything other than the already placed molecules in this density. However, this placed molecules, the phases from those can be used to find substructure, the sulfurs in the structure and chlorides, which gives you all the red bubbles. You're not quite clear which ones are sulfurs, although those two who are close to each other are certainly going to be sulfurs. But for example, for this one, we don't know yet. And then you take this and do anomalous phasing with those substructure that you've now gained from your molecular replacement. And that actually gives you 300 residues out of, I think, 360. And the outer trace looks already beautiful. The side chains are visible. This is what is considered a very good density, because in addition to seeing the trace covering the electron density actually covering the entire trace, if you look very closely at the edge of the alphas, for example, up here, you can already see the rest of the side chain. So seeing the rest of the side chain, or even seeing holes in aromatic rings, makes us super excited, because it usually means experimental phasing has worked. Now, ANODE is a program for validation, and it exploits experimental phasing, but it has nothing to do with it. It's something you do at the end, usually, to validate your structure. And it uses the anomalous signal to confirm the position of anomalous scatterers, or if you did isomorphous replacement, to see what has happened between two crystal structures or two data sets. So you take the intensity differences caused by the anomalous scatterers and the phases that you know after you've solved the structure, and you get an anomalous map. Now this map only shows you density in places where there were anomalous scatterers. So for example, this can help you to decide that the sulfate that you can see here is possibly not correct, or only partially occupied, because all the other sulfurs seem to have nice density, but this one does not. This can in particularly be helpful when you're trying to orient a ligand, by the way, for example, a barium-containing ligand. And you can also make different maps, for example, from RIP density. So this is a disulfide bridge. In the data set before the radiation damage occurred, the sulfurs were bonded to each other. In the one after, you can visualize that they flopped away as the bond was broken by X-rays. This brings me at the end of this hour to a summary. Experimental phasing methods make use of marker substructures of certain elements to solve the phase problem via the phasing equations. Patterson maps can help. They basically exploit intensity differences between two datasets or within the same dataset. MAD and SAT exploit the anomalous signal from one or more datasets from the same crystal or the same type of crystal. SIR and MIR utilize several heavy atom-soaked derivative crystals. These crystals have to be isomorphous in order to be used. Experimental phase solutions do not define the enantiomorph. After solution, you have to apply density modification and choose the map that looks like protein. The only exception from this is when you use the molecular replacement solution in what is called MRSAT. Well, that's so far from me. And I'm very happy to take your questions. And next week, we are going to talk about refinement. From Sam Harrell to everyone, what happened to SHELXC and B? No one knows, and no one is speaking about SHELXC and SHELXB. But perhaps you will be daring enough to write George Sheldrick an email and ask him. So I have been doing my entire PhD working on SHELXC, and I never dared to ask.